We can't talk about solutions without talking about math. There's all sorts of different concentration terms we can use. Now, molarity, that one at the top, this is the one that we most commonly use in chemistry. This is our moles of solute over our liters of solution. Then we have molality with that little lowercase m. That's still moles of solute, but now we're looking at kilograms of our solvent. We use this one more frequently when we talk about colligative properties. Mass percent, mass of the part, the solute, over mass of the whole, the solution, times 100, that gives us a percent. And then we have some related ones with mass volume percent and volume percent. Then we get into our parts per million and parts per billion, which are very similar to mass percent, except instead of being multiplied by 100, they're multiplied by 10 to the 6th and 10 to the 9th. These are commonly used in things like environmental considerations, because if I'm looking at drinking water or a river or a lake, and I want to know how much of something is in those, I probably don't want a whole lot of stuff contaminating it, so I'm hoping that they're in very small amounts. Mole fraction, moles of the part over moles of the whole. So we take the moles of the solute over the moles of the solute plus the solvent. So our first example, we're going to start off relatively simple with a mass percent here. On my balance, I've weighed out 8 grams of potassium chloride. I've then just simply added water until I've reached 50 grams. So what's our mass percent of potassium chloride? All right, so our mass of our part is our 8 grams. Okay, we did this directly on the balance till we got to 50 grams. So we already know the mass of our total solution. And then we multiply that by 100. And what we end up with is 16% potassium chloride. Okay? All right, now this one, I've got a solution where I have 31.7 grams of silver nitrate in 52 grams of water. Now that 52 grams is not the whole solution. That's just the grams of water. So to get my mass percent, I have to take my mass of my part over the mass of my whole. So that's going to be my 31.7 plus my 52 times my 100, and I'm going to end up with 37.87% silver nitrate. Okay. Now we can use mass percent as a conversion factor. So here I've got a paint that needs a certain amount of iron 3 oxide to give it the correct color. So I have a solution that's 30% by mass iron 3 oxide. So what does that mean? My 30% by mass. What I can say is that I have 30 grams over my solution. So I can use that as a conversion factor. Okay, so from my problem, I need 42.8 grams of my iron 3 oxide, and I need to know how much solution. So I have 100 grams of solution for every 30 grams of iron 3 oxide. So I get 142.6. I have 3 sig figs, so I need 143 grams of solution. So I can use that as a conversion factor. Okay, all right, here I want to know the mass volume percent. Okay, so again, mass volume percent is our mass of solute over volume. And this is in milliliters, and that's times 100. Okay, so we have our mass of our solute, we have our volume of solution. So I have 24.1 grams of cadmium chloride and 250 milliliters of solution times 100 gives me 9.64% by volume cadmium chloride. Okay. All right, again, we can use this as a conversion factor. So I've got this 2.65% mass volume of sodium alginate. All right, so what that tells me is that I have 2.65 grams. I'm going to abbreviate it as NaAlG for every 100 milliliters of solution. Okay, so I need 0.45 grams of sodium alginate in each scoop of my little solution. So how many mils do I need to add? Oh, where'd my extra slide go? Oh well, I'll just do it here. And so we would need 16.98. We have 2 sig figs, so I'd need 17 mils of solution. Okay. All right, now, when I prepare a solution, again, we weigh it out. We put it into whatever container we're using. We dissolve it. And then once it's dissolved, we fill it to the line. This is what we do, especially when we're making solutions of a particular molarity. All right, and so molarity, remember, is moles over liters of solution. So if I weigh something out accurately on my analytical balance, I get a mass. If I have a mass and I know the compound, I can calculate the molar mass. And from the molar mass, I can get the moles. And so that tells me how many moles I have. And then something like this is a volumetric glassware, a volumetric flask, and it is usually hand blown and hand calibrated, and so it's known to really good accuracy and precision if you fill it correctly to the line. All right, so molarity, again, is that moles of solute over liters of solution. Okay, so I have grams and I have milliliters. So I have to do some conversion. So I take my 57.0 grams of sodium hydroxide and I convert to moles. So the molar mass of sodium hydroxide, I have 39.98 grams per mole. So I have 1 mole sodium hydroxide and every 39.98. And I get 1.43 moles sodium hydroxide. And 300 mils times 1 liter in every 1,000 milliliters gives me 0.3. Okay? So now I have the right units to solve my problem. So I'm going to take my 1.43 moles of sodium hydroxide over my 0.3 liters, and I get 4.75 molar sodium hydroxide. Okay? All right. Now I have a 2.50 molar solution of sodium acetate. I want to know how much volume of that solution will contain 0.650 moles of sodium acetate. So again, this is moles over liters. So what I'm going to do, I'm going to take my 0.650 moles of sodium acetate. I have 1 liter of solution in every 2.50 moles of sodium acetate. So this right here is that molarity. Okay? Now, this asks for volume in milliliters. if I were to stop here, I would end up in liters. So then I have to do 1,000 milliliters in 1 liter. And I will get 260 milliliters of my sodium acetate solution. Okay? All right. Okay, so now I want to calculate the molarity of hydrobromic acid, where we've dissolved hydrogen bromide into water. So I have 455 mils of this acid that has a 1.8 moles of hydrogen bromide. Okay, so pay attention here. Again, molarity, moles per liter. So my 455 milliliters becomes 0.455 liters. Okay? So then I take my 1.80 moles of hydrogen bromide over 0.455 liters, and I get 3.96 molar hydrogen bromide, or hydrobromic acid. Since once you dissolve that in water, this one becomes an acid. Okay? All right. So now I have this solute. So I want to know how many grams of solute are in this solution of sodium monohydrogen phosphate. So my molarity is moles per liter. I need to know grams, so I'm going to need to know that molar mass. So when I calculate the molar mass here, we get 141.962 grams per mole. Okay? So now we can go ahead and solve this. So we're going to go from a volume to moles over to grams. Okay? All right, so I have 1.75 liters of solution. My molarity tells me that I have 0.460 moles in every 1 liter of my solution. And then I have 141.962 grams in every 1 mole. Okay? And so I get 114 grams of my sodium monohydrogen phosphate contained in that amount of solution. Okay. Let's try a molality one. Again, molality is the moles in kilograms of solvent. Okay. So I need to convert my calcium chloride to moles. So 32.0 grams times 1 mole of calcium chloride. The molar mass is 110.978. Okay, we're going to get 0.288 moles. Okay, we also need kilograms. So I've got to do a conversion here. 271 grams times a kilogram in 1,000 grams is going to give me 0.271 kilograms of my water. Sorry, I just got startled. I think my daughter has arrived home and somebody just banged on my door and knocked me off guard. So if I flailed, that's because my door is being knocked on. All right, so now I have moles and I have kilograms, so I can solve for my molality. So I'm going to take my 0.288 moles of my calcium chloride, and my 0.271 kilograms of my water, and I'm going to get 1.06, and this is lowercase m because it's molality. So we say this is 1.06 molal calcium chloride. Okay? So when we go back and forth on these units, okay, if we're using, mole to mass, we need molar mass. All right? We've done these before. If we're going mass to volume, sometimes you need density. All right? And then our molality gives us a quantity of solvent, whereas the rest of these involve a quantity of solution. So you have to pay attention to the different units. When we have our solutions, sometimes we need to change their concentration. And so that's where dilutions come in. All right. So dilutions, we have this M1V1 equals M2V2. So what we're doing is we're taking the concentration of our more concentrated solution and a volume of our more concentrated solution, and then we are making a less concentrated solution. Now, when we do this, the M1V1 equals M2V2, because all we're doing is we're changing the volume. So we're adding more of our solvent. So the moles the total moles of solute don't change when we dilute. The concentration does, though. Okay? So in these two pictures, I have the same moles of solute. It's just in the first one, I only have a little bit of that. But now when I add more of my solvent, now they're more spread out. And so it's a more dilute solution. Okay? All right, so we've got more solute particles per unit volume in a more concentrated solution, and then fewer in a more dilute solution. Okay? Now, one of the nice things is when we do dilutions, normally for molarity, we have to leave everything in liters. All right, we can't have milliliters. But with the dilution equation, the way the units cancel, you can actually, and the way everything's a proportionality, you can actually just leave things in milliliters. Okay? Here we've got liters though. I've got this isotonic saline. It's a 0.15 molar solution of sodium chloride. We want to prepare 0.8 liters of this from a 6.0 molar stock solution. So when I do these, I like to define my variables. So my stock solution, so my M1 is my 6.0 molar. Okay? It's asking how would we prepare it, so we don't know how much of that stock we need. Our target is the 0.15, and our target is the 0.8. Okay? So I like to define those variables so I can keep them straight. So again, we have M1V1 equals M2V2. And here we're solving for V1. How much of that stock solution do we need? So V1 is equal to M2V2 over M1. And so then it's a matter of plugging it in. So I have my 0.15, I have my 0.8, over my 6.0. And so molarity and molarity cancel, and we're left with that volume. And we get 2.0 times 10 to the negative 2 liters, which works out to 20 milliliters. Usually we do things in milliliters because that's what most of our glassware is in. So what I would do is I would measure 20 mil of 6.0 molar stock, and then add, if I need a total volume of 800 liters or 800 milliliters, I would add 780 for a total and that 800 milliliters is the 0.8 liters. Okay, and so we would add enough to get up to that total volume. All right, here's another one. All right, so take a look at this one. Try to solve it. I'm just going to give you the final answer. So you're trying to figure out what the M2 is, the second molarity. All right, you should get 0.6 molar potassium chloride solution. All right, so these are our different solution concentrations, and then what we do when we need to make a different concentrated solution.